All right, here's yet another example in log decrements type stuff. And the source of this is Inman, which is a pretty good book. I like it. I've used it before. The free response of the damp single degree of freedom system in this figure right here. Well, I think it's. Oh, I guess that figure is just a little spring and damper thingy going on right there. Yeah. It has a mass of 2 kilograms. Is recorded to be of the form of figure 135. Okay, so here's the figure right here, that one. A static deflection test is performed, and the stiffness is determined to be 1.5 or 1,500 newtons per meter. The displacement at T1 and T2 are measured to be 9 and 1 millimeter. Successfully calculate the damping coefficient. So here's yet another combination of things put together to create a damping system. So I think I can maybe write all this stuff on here, and maybe I could squeeze it on here so we have the relevant stuff. The K is equal to 1,500 newtons per meter. And so basically what we're trying to find is C from this. We see that this thing is 9 and 9. So right here, they're not actually showing this correct. Okay, so this is just an example one. This is not the actual one. But right in here, they're saying at that point, we get 9 millimeters. And here, we get 1 millimeter. Right here. So they don't tell us anything else besides there. But we can, from this, we can get the log decrement, which is going to be the natural log of, well, let's just go 9 over 1. I'm not going to write out the equation again. But this is just 2.197. We can get, but from here, we can get the natural, undamped natural frequency, K over M. All right, I don't have to plug those in right there. We could just say what the number is, because you have 1,500 divided by 2 square root of it. You can plug that in yourself and get a 27.39. It's kind of funny. There's a lot of problems when I wrote out the problems for this associated with these topics. They all had the same range of natural frequencies of right around 27. It's really kind of like, I don't know what the magic is right there. But anyway, let's see. I didn't need. That's something I'm going to need, but I could have also just continued with my log decrement thing and said taking the log decrement and divide it by 2 pi squared plus log decrement squared, right? And once again, I could stick that number in there, but you could get the number too. And you get 0.3301, which is actually really close to what another example previously was. That's kind of weird. All right, so with though, I'm jumping around here because I could have done this other thing. Okay, so I have the damping factor. I need the critical damping to go 2m omega n, right? So which is 2 times 2 times 27.39. In a previous video, I made the units work out. So if you want to look at that, 109.6, and they should be a Newton second per meter. So therefore, we can find by taking the damping factor times the critical, we can find out what the value is going to be. So it's 0.3301 times 109.6, and we get the 36.17 Newton second per meter. Almost dropped wrong thing. So here is the thing that we want to get. And that's my last example for log decrement type of things. The next topic is Coulomb damping within this week. I don't know how much I will do. How much? I don't think there's as many problems. I do have something written in my notes about this that I'm a little concerned about. So I think I'm going to ask Dr. Bob. Yeah. All right, so that's a lot of examples.